Welcome to solverfy.
This is the answer to Chapter 15, problem number 81 from the Smith Organic Chemistry textbook. And this problem asks us about the triphenylmethyl radical. We're told that it's unusually persistent in solution, so it sticks around for longer than we might expect for a radical. And we're also given these two structures, hexaphenylethane and molecule A. And so molecule A is the actual dimer instead of hexaphenylethane. And so we're asked four things about this. Why is triphenylmethyl radical more stable than most other radicals? We're asked to show how the dimer forms. We're asked to propose a reason for the formation of A rather than hexaphenylethane. And then we're asked how we could use proton and carbon NMR to distinguish between hexaphenylethane and A. Okay, so I'm just going to dive into this. So for A, the triphenylmethyl radical is very, very resonance stabilized. And so just to draw that out, so if we have this, and I'm just going to use pHs rather than draw all three rings. So here we go. So if the radical is right there, there are many, many resonance structures that we can draw here. And so we can draw one just by moving the bonds around the ring. So moving the double bonds around gives us this resonance structure with the radical still on this carbon. And then we can draw all the resonance structures where the radical is moving around the ring. So, for example, we can draw a double bond here and put our radical here. And then we can, like I said, just move it all around the ring. So now the radical's here. And we can do one more. Oops, it's not right. We can do one more. There we go. Where the radical is here. Okay, and so we have all of those resonance structures available to us for all three of the rings. And so this is obviously a very, very highly resonance stabilized radical. And so that's going to contribute quite a bit to the enhanced stability of this radical. And then the other thing is we have a lot of steric hindrance here with three aromatic rings. And so there's not going to be a lot of reactions that this molecule can undergo because it's hard for another molecule to get close to it. Okay, so that's part A. Part B used curved arrow notation to show how two triphenylmethyl radicals dimerize. Okay, and so in order to do that, we can draw this. So again, I'm going to use pHs for two of the rings. And then for my third ring, I'll draw it out. So if we start here and our radical is there, we are going to have something like this go on. Okay, and so after that movement of electrons, we will be at the resonance structure that looks like this. Draw the ring a little bigger so it's a little easier to see. So we have this going on, and now we have our radical on the carbon that's actually going to undergo the reaction here. And so we can draw another of our radicals. So this time I'm just going to use 3 pHs to symbolize the rings. So if we have this radical here, these can now react like this, come together to form a new carbon-carbon bond. And so that is going to give us molecule A. Okay, so there's the curved arrow notation. So then what are we asked for C? Propose a reason for the formation of A rather than hexaphenylethane. Okay, so hexaphenylethane is sterically disfavored to a large degree. So we have two very sterically hindered tertiary radicals that would have to come together. And then the other thing is for A, for molecule A, instead of that, instead of two tertiary radicals coming together, one of our radicals is situated on one of the carbons of one of the 6-membered rings. And so it's much more accessible for the tertiary radical of the other monomer that's going to form this dimer. They can come together much more easily because of sterics, because of crowding around those tertiary carbons. Okay, so then for D, we're asked how could proton and carbon NMR spectroscopy be used to distinguish between hexaphenylethane and A. And so I've drawn them out here. And so one thing that we can do is, well, we can think about for protons. So for proton NMR, for hexaphenylethane, we're only going to get aromatics. So we will only get aromatic signals. For molecule A, the proton NMR molecule A is going to have aromatics, but it's also going to have alkenes, and it's going to have just one sp3 hybridized carbon. So one hydrogen on a carbon, an sp3 carbon. And so that's going to be this guy right here. So there's that. And then also there's going to be alkene protons here and here and here and here. And so we can use them to pretty easily distinguish between these two molecules because molecule A is going to have alkenes and one hydrogen on a sp3 carbon, and hexaphenylethane is only going to have aromatic protons. And then the other thing that we could do as far as carbon NMR, we can count the different types of carbons. So hexaphenylethane looks like it's going to have 5 different types of carbons. whereas molecule A, if we start here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So obviously, we should see a lot more signals for molecule A than we would for hexaphenylethane. More than 9. I just stopped counting. So 10, and then all the aromatics. It might be hard to differentiate the aromatics since they're going to be in very, very similar environments to the other aromatics, but they would probably still give their own signals. But again, we're comparing at least 10 carbon NMR signals to only 5. And so let me just write that down. So 13C, 5 signals for the hexaphenylethane. And for molecule A, 13C is going to be greater than 10 signals. So again, very, very easy to distinguish just by looking at it, which molecule you have. Okay, so that's kind of a lot of information in this question. But again, here's the NMR stuff, and then here's parts A, B, and C. And that's the answer to chapter 15, problem number 81.